Okay, good evening. Okay, let's get started. This is the last lecture, and this is a general subject for industrial noise control. At least you know how to make use of the previous acoustic or standard calculations to do the analysis. In this one, I just want to share with you some general requirements and how to reduce the noise effects in industrial areas. Okay. In the last lectures, I told you that to compare with construction's noise control and industrial noise control, normally construction's activities we are doing outdoors. For industrial noise control, mainly we would do it indoors. So that's when we control the industrial activities, actually it is more easy to control external works. Okay, there are numbers of sources it could generate noise effects inside buildings, such as pumping system, equipment, pipings, and ventilation system. All of them, they could generate the noise effects. Okay, when you refer to some old districts in Hong Kong, you can see this one. Okay, this is a kind of heat exchange device. Okay, for air conditioning system. Okay, and even at the rooftop, even in poly buildings. Okay, you can see that there are many industrial equipments. We would place it, install it on the rooftop. So that's when we put it outside buildings. Even we put it on the rooftop. This is an outdoor areas. It could generate noise effects and it could affect the neighboring buildings. So noise from outside equipment often propagates to the communities, and noise generated from industrial activities or commercial buildings should comply with noise standards. The use of relevant technical memorandum. Okay, guidance. There are two general guidance for us for our analysis, for our study. The first one is good practices of pumping system noise control. This is to make sure that the public measures will be taken to avoid noise problems in designing pumping system and locating pumping equipment. And the second one is good practices on ventilation system noise control. This is to make sure that the public measures will be taken to avoid noise problems in designing ventilation system or locating ventilation system. When you go through these two documents, the working principles are very simple. Okay, they just share with you some general guidelines. Actually, in the previous lectures over across this semester, I already explained to you that how to make use relevant control measures for airborne noise and how to make use of the structural isolation system to reduce the structural noise. And also, if you want to study the noise controls for the ventilations or the air conditioning systems, you may refer to this guideline. This is what we call the ASHRAE handbook. One of the chapters is about sound and vibrations control for ventilation systems. There are some tables or there are some figures, information presented in this ASHRAE handbooks. But please pay attention. This one, the major purpose is to design the air conditioning system, not to reduce the sound and vibrations control. This is one of the chapters, along with the design guidelines, how to reduce the sound effects. Because you know that when we have an air duct, now when we turn on the air conditioning system, okay, we can listen to the sound effects, okay, inside this lecture room. Okay, when you turn it off, the sound effects could be taken out. So in terms of the pumping systems control, this is generally recognized operations of pumping system. Pumping system, it is relevant to the water flow, not airflow. Okay, this one is a pumping system. And the equipment noise control, no matter this is indoor or outdoor environment, equipments, they are noisy, and effective solutions is to suppress the noise emitted from them, so that we control it from the source. Okay. And the ventilation system noise control, if there is an airflow inside the ventilation ducts, it could generate noise effects, and this is unwanted noise effects, and we want to reduce it, such as we use an other layers of material, such as the absorptive materials, to encode it. Okay, similar to a leggings material. Okay, positions of equipment. Normally we could put it inside an enclosure or small plant rooms for those equipments. Equipments in a room with fitted wall or greater distance from the receiver. The receiver here, it refers to any buildings, okay, such as when we put an equipment on the rooftops or buildings, okay, we want to minimize the sound effects generated from these equipments to the adjacent buildings. And this receiver is the noise sensitive receiver. And behind some large enough structures, such as we may use a partial enclosure or partial barriers to reduce the noise effects. And the second approach is to select quiet equipment, such as we may use quiet equipment. We have the innovative design of these equipments to reduce the sound effects. And the schedule of maintenance, you know that all of them we are talking about mechanical devices or mechanical components. We need to do maintenance within a period of time. Okay, maintenance is one of the issues to reduce the noise effects. So as per usual, we could divide into 3 ways to reduce for the noise plannings against relevant noise problems, such as we sequentially use those equipments, or from the source we replace it when it get older. And the path, we may make use of the barrier, enclosure, or vibrations isolators. Please pay attention. The first 2 types, barriers and enclosures, they are used to reduce airborne noise, and the vibrations isolators, which are used for reducing structural noise. And the receiver, receiver is that enclosure with installations of ventilation equipment, so that these are the general pathways to reduce the noise effects. Okay, we go back to the original. Is that we could classify into 2 types. The first one is airborne noise, and the second one is structural noise. Because in these subjects, we are talking about those machines. No matter we use the operating machines, rotating machines, you could generate noise effects into 2 types. The first one is airborne noise, and the second one is structural noise. For the airborne noise, when it refers to the term here, it refers that noise arrives at a point of interest by propagation through air. And structural noise, it refers that noise arrives at a point of interest by propagation through a solid structure. Okay, we took 3 lectures to go through how to design an effective vibrations isolation system. At that time, I told you that when we want to control the structural noise, most of the time it is rather difficult to control these types of noise effects than that of the airborne noise. Airborne noise is so sometimes it's so simple. So we may make use of some acoustic materials that can help us to absorb those effects, or we may use the barriers or enclosures. But in terms of the structural noise, when we generate noise effects such as structural vibrations, all the connected structures could help transfer those vibrations energies. Okay, until it goes to the continuations of these structures. So it is rather difficult to control the propagation path. Okay, this one I just extracted these figures from the mechanical and electrical equipment for buildings. Okay, reference books for the designs of building structures or the electric M&E systems. When you take a look on this one, there are different approaches to reduce the noise effects. For example, this one, inertia blocks. Inertia block, we install inertia blocks to support this mechanical equipment, and also below that, underneath this inertia block, we install metal springs. Okay, I already explained to you that if we just install metal springs below this one, we can only reduce certain amounts of vibrations energy. But with the presence of the inertia blocks, we can further reduce it. Okay, minimize it. It is similar to what we call the floating slab track. Okay. Even in various designs, the vibrations energy. Okay, below the floating control we still have to install metal springs. Okay, otherwise, if we do not install these metal springs, what they look like, it is similar to a total mass. Okay, the force may be directly transferred, generated from this mechanical equipment to the supporting structure. But if we install these metal springs, it performs as vibrations. Okay, to transfer from one energy to another energy. So that this is a good combination of using the inertial block and also metal springs. Okay. And also inside this room, you consider we may make use of the acoustic types of walls. Okay, these acoustic materials we can use it to absorb interior noise effects. And also you consider there is a flexible boots or the flexible joints. Why we need to use this one? When this boiler is under operation, it could induce vibrations. Okay, with the presence of these flexible joints, it disconnects the vibrations energies that can be transmitted through these structures to the outside. Okay, because you may regard this as an other kinds of vibrations resistance design. This one. Okay, the first one is the piping system. For the piping system, in this guidelines, we could divide into 2 types: airborne noise and structural noise. They also highlights the major causes of those noise effects. For the piping systems, we are talking about the water flow inside those piping systems. Okay, this one, not airflow, water flow. Okay, when water flows inside a pipe, you could generate when this pipe, it means that the noise effects, okay, the noise effect that can be generated, and the water flows in the pipe that can cause vibrations at the pipe wall and generate broadband noise. What does it mean, broadband noise? It means that it is composed of different frequency effects. Okay, not just particular frequency. And water flow change direction suddenly because of the obstacles inside pipes. Let's say there are some other obstacles around the end here. It could generate the noise effects. And we can, because when we design a pipe here, we may make use of some valve. Okay, valve is a mechanical device to control the water flow, and it becomes louder with increasing water flow rates or the pipe size. So they propose this. They proposed a number of control remedies. The first one is to make use of a larger radius, so that you can minimize the vibrations effects. The second one is the use of the rigid mounting, okay, to prevent the vibrations effects generated from this water flow. And the third one is to use a large pipe or adjust water flow velocities to below 2 meters per second to reduce the water flow velocity. And the last one is the pipe linking. Pipe linking is to use added materials to surround to enclose the water pipe. So when you go through the information presented in this 2 slides, the proposed control remedies, so the information is very general, okay, just depends on common sense. We can achieve this one. Okay, the second one is the structural noise. Structural noise is due to the water flows. You could induce the vibrations of this piping system. So that's the direct approach is to use the direct mountings, okay, to secure the pipes to restrict the motions of them. And The pipes in direct contact with walls or slabs when the vibrations activates the building structures to generate noise or cause disturbance to residents inside buildings. So that any direct contact, let's say here along the wall or it penetrates the wall, okay, it could generate if there is any vibrations effects, it could be favorable in the transfer of noise effects, vibrations noise effects. So the first one is to make use of different types of vibrations isolators, such as the common one is to use the spring isolator. The second one is to use the rubber isolator, or we may make use of the rubber slave. Rubber slave is a kind of material, a soft type of materials. Okay, we could put it in between the wall and this pipe. Okay, in order to reduce the vibrations effects. And we can isolate pipes when they penetrate slabs or walls by compatible materials, such as the use of the rubber slave or glass fiber. Another final control remedy is to install pressure reducing valve. This one is a mechanical device. We can make use of a pressure reducing valve to control the water flow, the pressures of the water flow inside this one. We can also make use of the resilient pipe handlers. Okay, this is the pipe handlers or the rigid mountain. Okay, they are different types, but the working functions is similar to each other. Okay, no matter this is what we call the pipe hangers or the vibrations isolator. The major purpose is to restrict the motions of pipes induced from water flows. Okay, in terms of the mountain systems, we have the solid phase. Inside of solid phase, we just use this metallic device to secure the water flow. And the other one is that inside this metallic device, we also install the rubber isolators. And the third one is a common one, is the use of the spring isolator. Okay, the second type is the pump sets. Normally, we could put all these pump sets located on the rooftop, okay, because of the space issue. So when we put it on the rooftops, you could generate both airborne noise and structural noise. In terms of the airborne noise, you could directly generate it from this pump set machines to the adjacent buildings. The major source noise from that is from the mechanical components, okay, and the noise from a motor generator is the air movements induced by cooling fan. Okay, you can take a look on this one, this sessions. Okay, when the motor is in rotations, you could generate two types of noise. The first one is the bob band noise. Okay, what does it mean, bob band noise? It means that it is composed of different frequency components, okay, maybe from 20 hertz up to 20k hertz. And the other one is the discrete noise. What is the meaning of discrete noise? Discrete noise is a kind of specific or the particular noise, okay. In the first two lectures, I introduced to use that what is tonal noise, okay. Tonal noise is induced from the rotating machines. Why? Tonal noise, even in our experiments, we can identify some sort of noise effects. We need to make corrections according to the technical memorandum, correct? Why we have this tonal noise effects when we consider our rotating machines? The first one is the bob band noise, okay. It is, we can easily understand this part. How about the discrete noise? Discrete noise is created when the rotating blades, okay, hits on air particles to create a specific noise effects. Okay, I explain again. When we have a rotating machines, there are two types of noise effects. The first one is the bob band noise, okay? It means that under the airflow, okay, under the rotations of these machines, it could generate the bob band noise. The other one is what we call the discrete noise. Why it could create this discrete noise or the tonal effects? Because when the blades, rotating blades are in operations, it could continuously hit on air particles, okay? Let's say like this one. Okay, you can see that there is a blade. When the blades are in rotations, you can reverse the blue particles here. You can regard all these blue particles are air particles. When it is in rotations, okay, the blades hit on these air particles. When the blades hit on these air particles, it could generate a particular noise effect. Okay, so you could generate another type of noise effect, what we call the discrete noise. So I will let you know how to calculate this one for the power fan. The control remedies in terms of the airborne noise, we may do a regular maintenance for those mechanical components. The second one is to install a barrier, a partial barriers between the pump sets and the adjacent buildings in order to reduce the noise effects. And the third one is similarly, this is a kind of partial enclosures to limit the radiations of acoustical energies. Okay, for the second point and the third point, actually the working principle is the same, is to install an obstacle in between the source and the receiver. We can also to fabricate a complete enclosure with silencers to limit the radiations of acoustical energy. Okay, please pay attention on these provisions. When we build fully enclosed structures to cover these equipments, let's say like this one, okay, please pay attention that because under the operations of this motor, okay, you could generate heat effects, okay, so that we need to maintain a good airflow maintenance between inside and outside area, correct? Otherwise, it may induce overheating effects inside this enclosure. Or we may install this silencer. What is the major functions of this silencers? These silencers just allows the airflows between inside and outside in order to reduce the heat effects accumulated inside this enclosure. But with the presence of these silencers, it can also allow the reduce of noise effects, because when we zoom in into this silencers, there are many absorptive materials inside this one. When noise effects passes through these silencers, large amounts of noise effects could be absorbed by this acoustic lining materials. So that's why with the presence of this one, you can allow the airflows between inside and outside, but you can also help absorb airborne noise effects. Okay, when we install or fabricate a complete enclosure, please pay attention. We need to install a silencer here. There are two major purposes. The first one is to maintain good air ventilation between indoor and outdoor environments. The second one is that we want to limit the noise effects generated from the indoor areas to the outdoor areas. So that this silencers is a kind of discharge silencers. With the provisions of this one, you can help to reduce the noise effects. Another one is to locate pump set within the enclosed plant room. This one is essentially similar to this one. Okay, also is a complete enclosure, but the size is getting bigger or larger when we use a plant room. But when you compare these two figures, we still install the discharge silencers for these two provisions. Okay. Okay, another one is the structural bore noise. Vibrations from an operating pump set can be transmitted to interior areas of buildings. Let's say when there is a motor, the vibrations energies could be transmitted through this structure. So how to reduce the vibrations effects? The common one, the first one is to provide an inertia block. Inertia block is a kind of concrete pith. Okay, this is the concrete pith. For supporting pump sets, it can help add rigidities and stability to the pumping system. The second one, below this one or underneath this inertia block, we still need to install vibrations isolators. We need to combine these two approaches together. Okay, not only one for lightweight structures. It is okay when we just install vibrations isolations. But for heavy structures, it is recommended to install both of them to support the whole system in such a way that we can reduce the structural bore noise effects. And also, we propose the use of the flexible connectors. Okay, you can see that when you look at these figures, there are flexible connectors here because those connected structures could help transfer vibrations energy. So that these flexible connectors are used to terminate the propagations of vibrations energy with the presence of this device. Okay, and also when the operator is in operations, okay, airflow may follow this path, and then we have the flexible joints, and also the connected pump air ventilation. Thus, we still install anti-vibration spring handlers in such a way to resist the motions of this one. Okay, in terms of vibrations isolations, we talk many of them in 3 lectures. Okay, you learned this before. This is the transmissibility. Okay, the y-axis, and this is the frequency ratio. Please pay attention. Frequency ratio must be equals to this one. Okay, the external frequency derived by the natural frequency. And under the harmonic excitations, you can see that this is what we call the region of isolation. This is the regions of amplification. Okay, we don't want to go to this region. And this is the regions of isolations. We want to achieve this one. So that's what is the basic critical points we can achieve this region is this one, Wood 2. Okay, Wood 2 means that the transmissibility at least it is equal to 1. Okay, if it goes further, okay, it could decrease to this region. The transmissibility must be not higher than 1. Okay. Okay, so these equations, the natural frequency, I don't explain here again. Okay, you need to know how to calculate this one. This one is in terms of hertz. This one could not be given. Okay, you know how to calculate the natural frequency here. And this one is the external frequency. External frequency when we are talking about the rotational machines. The external frequency when we change it back in terms of hertz is the rotational speed in terms of RPM derived by 60. Okay, this is we can convert back to another units in terms of hertz. And this equation is transmissibility. If we have such kinds of problems, okay, these equations could be given. Okay. Okay, ventilation noise problems. Okay, airborne noise. This one is what we call the cooling tower. This device is what we call the cooling tower. When we go some old districts in Hong Kong, you can see this one. This one is for heat exchange. This is part of air conditioning systems. Okay, because we have limited space inside buildings, so that normally we put all devices outside the buildings. Okay, maybe at the rooftop. Like this one. Cooling tower is a kind of heat exchanger used for air conditioning ventilation system. The basic concept is very simple. Okay, you can see that when we go into the internal structures of this device, when water cooling inside the water cooling tower, the air is in this direction. Okay, and the water flows circulation is in other directions because of the interactions between the water and air. So that's why heat can be taken out. Okay. Noise mainly come from the air turbulence effect, a condenser fans. There is a fan here. Okay, if there is no fans, water cannot pass through from the bottoms to the upper parts. And water circulations inside the cooling tower can also create noise. Okay, how to handle this noise effects? The first one is that we may use the barrier. Okay, this is the barrier, and also we may provide some acoustic neighborhoods. Okay, this is similar to a small scale noise barrier. And also the airflow direction should not be directed to the adjacent buildings. Okay, on the other side. And inside the structures, we also provide some acoustic mats. Okay, to reduce the water slashing noise. In terms of the structural bore noise effects, similar approaches should be applied, such as the use of the concrete pith, and below the concrete pith, we can install some metallic springs, so that when we combine both of them, we are able to reduce the structural bore noise effects. And flow noise and vibrations from turbulence, sharp pressure drop, and traded air, all of this one could generate the noise effects. So when you compare the slides, the information presented here, you can find that this is similar to what we discussed for pump sets. Okay, so I cannot repeat too much about this one. I just want to share with you that how to do the calculations for this one. Okay, this equation is to find out the sound power level. This is sound power level, not sound pressure level. Please pay attention. Sound power level or a rotating fan. Okay, no matter this is a centrifugal fan and the SO fan. The difference between these two types of fans is the directions. Centrifugal fan is that the flow inside is in perpendicular to the flow outside. This is what we call the centrifugal fan. And the SO fan, it means that the flow inside the rotating race is in parallel with the flow outside. Okay. Okay, how to assess the sound power level for this one? The first one is LW on the left-hand side. On the right-hand side, the first one is the KW. KW, what is that? Is that under some specific conditions, we found out the sound power levels at that particular conditions. That means when you refer to this table, okay, we consider 1 octave. Do you still remember that what is 1 octave? This is 1 octave. When the frequency doubles, okay, it becomes 125 here. When we double 125, it becomes 250. Okay, this is 1 octave. And under some specific conditions, what specific conditions? The airflow rate 0.47 liter per second, and under 249 Pascal. Okay, these two conditions. Please, you can see that there are 2 terms here, the second one and the third one. The second one is Q0. The reference value, we take it as 0.47 liter per second. Okay, L here is liter. And the reference value is 248.8 Pascal, or we may say this is 2049, okay? Under these two conditions, we measure the specific sound power level under different fan types. Okay, let's say at 63 Hz, the centrifugal fans, let's say ratio rate is 48 dBA. Okay, these equations and this table should be given if there are some similar problems. Okay, but you just need to know how to make use of this information to calculate the sound power level. Okay, now we go to this one. BFI. What is BFI? BFI is the break frequency increments, or when you refer to some reference box, they could say this is break tone. How to find the break tone? When you refer to this figure, this table, there is a column here. This column is what we call the break tone. Okay. Okay, now you may ask the question that why we use 0.47 liter per second or 248.8 Pascal, these two conditions as a reference, not others. Because the test was conducted according to the United States system, US system. Before that, actually 0.47 liter per second is equal to 1 cubic feet per minute. At that time, they used these two conditions. The first condition is that 1 cubic feet per minute. When we change it in terms of this system, is 0.47 liter per second. And the second one is 248.8 Pascal. This is exactly equal to the pressure under 1 inch water column. Okay. Okay, this is just for your information. Why we take these two figures as our reference. Okay, so when Q is the volume flow rate and P is the total pressure, BFI is the break frequency increments or break tone, and Cn is the efficiency corrections. We can make use of these equations to find out the efficiency corrections. And this one is the hydraulic efficiency of the fan. You can follow all these equations here. And horsepower. 1 horsepower is equal to 746 watts. Okay, this is just for your information. Okay. Okay, now how to do the calculations? Let us go back to this one first. Okay, before that, I told you that when a braking system is in rotations, okay, there are two types of noise effects. One is the Bobel noise, and one is the discrete noise. Discrete noise is come from the force created from these brakes acting on air particles. Okay, so that it could generate, let's say like this one. Okay, the ventilation system is in operations now. Okay, so that it may be composed of different frequency components. Okay, now when I use my arm to hit on the chair, okay, you create another noise effect. You may consider that this is the rotational force or the rotational brakes hit on air particles. Okay, to create another particular noise effect. Okay, similar to I hit on the table. Okay. So how to do the calculations for this one? Okay, let's take a example here. We have a forward curved brake centrifugal fan with 55 brakes operates at a speed of 552 RPM against a pressure of 190 Pascal to deliver 1.8 meter cube per second air. We assume that the efficiency correction is not considered. We just need to estimate its sound power level at 250 Hz and 500 Hz. So we consider these equations. The first step we need to do this one is to consider the BFI. How to calculate the BFI? This is brake tone. How to locate this? How to find this one? It depends on the brake passing frequency. For the brake passing frequency, it is reference to the numbers of brakes. Okay, in the example now we have 55 brakes, correct? Okay, as given in the questions. The numbers of brakes times RPM, the rotational speed, divided by 60. This is the Hertz. This is the Hertz in terms of Hertz. Okay, now remember this formula. The first one we need to find out the brake passing frequency. The brake passing frequency under the conditions here is 55 times 552. 552 is the rotational speed. Okay, this is the rotational speed. Correct. The numbers of brakes in this case is 55, and the rotational speed under this case is 552. According to the formula presented in your lecture logs, we use 55 times 552 divided by 60. Divided by 60. The brake passing frequency is 506 Hz. Okay, any problem so far? Why we need to consider this one? Because this brake passing frequency, it is representative that under what region, frequency region, the tonal effects or the discrete effects could be generated. Now, the brake passing frequency is under 506 Hz. It means that when we consider 1 octave, 506 Hz is in this range, correct? Is in this range, 354 Hz up to 707 Hz. Okay, you can go back to this one. This is the lecture logs for lecture number 1. Okay, basic concept. For 1 octave, the frequency bandwidth is from f divided by root 2. This is not minus sign. This is 2. Okay, root 2 times f. You can check it by yourself. If you substitute 500 into this equation, 500 divided by root 2 is approximately equal to 354. Okay, this is 1 octave, and this is 1/3 octave. And if this is 500, the range is from 353 up to 707. Or you can make use of these equations to find out the range. The first one we locate the brake passing frequency is at 506 Hz, so that we can decide that the brake tone effects could appear within this region. Okay, in this region from 354 up to 707 Hz. Okay, I explain again. 506 Hz is within this range. So when you consider the sound power level within this region, we need to make a corrections. Okay, now what is the fan type in this question? The forward curved brake. Okay, this one, correct? So the corrections factor is 2. The corrections factor is 2. But please pay attention. The brake tone or the BFI is just applied. We just apply 2 dB corrections to the 500 frequency octave band. What does it mean? It means that when you consider the frequency value within this range, you need to make these corrections. Outside this range, you don't need to make correction. Okay, BT is equal to 0 dB for all other octave bands. Okay, just within this region, we need to make 2 dB corrections. Outside this range, let's say the frequency now we consider is 300 Hz. We do not need to make this correction. Okay, so refers to the questions. The 500 hertz kW, when you refer to this one, at 500 hertz kW, the value is 34. Okay, 34. And how about the flow wave? The flow wave is 1,800. Why is 1,800, not 1.8 meter cube? Why? Because the reference value is here. The reference value here is 0.47 liter per second. When you do calculations, you need to make use of the consistent units. Okay, 1.8 meter cube per second is equal to 1,800 liter per second. Okay. And the pressure is 190, so you just put it into 190. BFI, according to the statement here, is equal to 2. And CN, we can ignore CN because it is not, the question tells us that we don't need to consider this one. So at 500 hertz, the sound power level at this particular frequency, it becomes 69.5 dB. Okay, how about at 250 hertz? At 250 hertz, when you refer to the data here, kW, it becomes 38. The flow rate and the pressure, they're the same, but BFI is equal to 0 because 250 hertz is outside this domain, frequency domain. Okay. This one is used to correct the break tone effects. Okay, outside this one, we assume that yes, it is not the range we can achieve the break tone effects. So that's the correction factor BFI here is equal to 0, and then you can calculate that the final result is 71.5 dB. Okay, if we want to find out the total sound power level, what does it mean? It means that we need to consider all the sound frequencies here from 63 hertz up to 8K hertz and then sum up together. Okay. Any problem about how to do the calculations here? When you take a look on this one, the first procedure, you need to find out the break passing frequency because these results can help you to locate the regions where is the frequency domain we need to make corrections to these parts. Okay. Let's say if we find that the range is below 350, we need to consider which optic-band we need to apply for the frequency corrections. Okay. I explain again. The first step you have to do is to find out the break passing frequency. This one can help you to identify the frequency region where break tones occurs. After that, you can select. You can use this table to select the correct break tone corrections factor. Let's say here there are different band types. This is the forward curved wave. The corrections factor is 2. For example, the tubular is 4 to 6. Okay, you may select an appropriate values within this region, not outside this region. Okay. Any problem? Okay, let's celebrate. If you have any problems about this example, you may ask me. Okay, this is the various samples to show you how can find out the sound power level. Please pay attention. This is sound power level, not sound pressure level. Sound power level, it depends on its original source. It means that the acoustic energies that can be generated from these rotating machines. This is sound power level. Okay, when we are talking about the sound pressure level, we have a distance. Okay, we have a receiver. Okay, so please bear in mind that the calculations here, they are used to find out the sound power level. Okay, now we go back to this one, the ventilation noise problem for the airborne noise. This is not the piping system, this is the ventilation system. Ventilation systems are used to transfer airflow, okay, in order to maintain the good indoor air qualities within buildings. And air flowing through ducts can favor the vibrations of ducts, what generates noise. The second one is the noise inside the ducts can be directly transmitted to the ambient environment through the duct surface. Okay, how to reduce the noise effects? We may stiffen the vibrating duct surface with supporting straps. This one is supporting strap. Or to reduce the movements of the vibrating surface. The second one is to use some damping materials to the vibrating duct surface or the use of the composite ligands or sound absorbing materials. So when you compare all of them, they are very similar to each other. Okay, the second one is that even the locations of our regulator, the regulators can control the amount of airflow, okay, or even the speeds passing through air duct. Okay, you can see that if the regulator is too close to this rotating vent, okay, turbulence could occur. Turbulence is a major source to induce noise effects. Okay, even in very noise studies, I told you that turbulence is the key components to create louder very noise effects. So then, how to streamline those airflows in order to prevent or minimize the occurrence of turbulence? This is the key concept. So that's why at the head or at the tail of the train, okay, we make it streamline. Okay. So in this way we may make it with sufficient separation distance in order to reduce the formations of turbulence inside this one. And the other one we may use the curved band instead of using the suddenly change of the directions, floating direction. Okay, the table here I just extracted from this X-ray handbook. This is a kind of a well-known handbook for air conditioning system design. You can see that this is the diameters of the round ducts under the 1 octave, the insertion loss by optic band center frequency. What does it mean, insertion loss? Insertion loss is that we measure at the same distance without this material, and with this material we compare at the same distance. This is what we call the insertion loss. Okay. This is another one is for rectangular metal ducts, and then I list out all the components here. What kinds of control remedies we are able to use it to reduce the noise effects. For example, the air cool chiller. Chiller is a kind of heat exchangers. And for the water cooling tower pumping system, we can make different. We can select one of the options, or we may combine all of them together in order to reduce the airborne noise and also the structural noise. They also presented in this document. They also presented guidelines. The noise. If we want to achieve the noise exceedance levels less than 10 dB, we may make use of the barrier. If we want to use more than 20 dB, we may make use of the complete enclosure or silencers or something like that. This is just the recommended practical remedies. Okay, now another one is the noise predictions of ventilation machines. This is another document. This is also a simplified airborne noise predictions approach for ventilation machines, given in the good practices in ventilation system noise control. Okay, let's take a look how to do this one. There are 5 major steps. The first one is to identify the most affected noise sensor receiver. Okay, this is very basic or fundamental, because you know that if there are no any noise sensor receivers, actually we don't care about the noise problem. Okay. The second one is the sound power levels for noise source, and the third one for the sound power levels of different sources, you can refer to this table. Okay, the first one is for air cooled chillers. Under different cooling capacity, they have different sound power levels. We just read these guidelines to assess to do predictions. The second one is typical sound power levels for water cooling towers, and the last one is typical water power levels of fans under different pressures, 125 Pascal or 750 Pascal. The third one is distance attenuations. Please pay attention to the attenuations here. They are all negative values, okay? Because this one is the attenuation. Attenuations means reductions, okay? So that if the distance, let's say, is 10 meters away from the source, it means that the attenuation factor is minus 28 dBA. And then the summations of noise level. Okay, I explained this one before to you when we were discussing in construction noise. When there are two sources, the difference, let's say 2 to 3 dB, we have to select 2 dB and it add up to the highest level. Okay, if we want to find the overall level, we do not need to do the calculations by using formulas. We can directly make use of this table to do analysis. And the last one is that if this is an NSR, in case NSR is a building, positive corrections of 3 dBA for acoustic reflection should be applied. Okay, to the step number 4. Okay, now there is an example for you, in-class assessments. Please read through the information here. We have two devices, and then one is 20 meters away from the NSR, and the other one is 25 meters from the NSR. Assume that the acceptable noise level should not be more than 65 dBA. Okay, first of all, you need to find out what is the sound power pressure level at the receiver, and if it is, and the second one is that whether it is acceptable within some pressure level. Okay, please take about 5 minutes to go through this one. You just need to follow the 5 steps presented here. Okay, let's check the answer. Okay, we follow all 5 steps here. The first one is that the residential building is the most sensitive receiver. So the second step is that the sound power level for power fan is 99 dB according to the table presented in the document. Okay, and the chiller is 105 dBA. Okay, you can select the information here. Okay, you can select the information here, the air cooler chillers and also the power levels of fans. Okay, one is 20 meters away from the building, so that according to the table, the distance attenuation is 34 dBA. It becomes 65 dBA. And the second one is 25 meters away from the building, so that the sound and sound pressure level it becomes 69 dBA. Okay, now when you compare this one, the difference is 4 dBA. So the correction factor, we can add it to the highest one, 69 dBA, it becomes 7.5 dBA, 17.5 dBA. We haven't finished. We still have step number 5. Step number 5 is that because this is NSR is a building, so that we need to add 3 dB to the level we got it from step number 4. So this is the total one, 73.5 dBA. When you refer to this one, this is higher than 65 dBA, it means that it is not acceptable, correct? The calculated purchase level is more than 8.5 dBA than the acceptable noise level. So you may think about that, how to reduce this one by using the provision CS. Okay. Let's say if we want to just reduce 8.5 dBA in this case, we may make use of the barrier, or we may make use of the complete enclosure with silencer. Okay, something like that. These two are just suggestions only. Okay. These two selections are just suggestions only. Okay, you can select other options. Okay, now we go to the last topic in this lecture is the factories and industrial undertakings regulations. Okay, please keep quiet. Okay, this document was issued from the Labor Department. Okay, not EPD. This is about, because we are talking about the industrial areas. They are relevant documents and issued from the correspondence departments. And this one was issued from the Labor Departments. And what's the usage of this one? It provides requirements or regulations or protections or hearings or employees in industrial undertakings. That means under what conditions we need to present or we need to enforce workers to wear specific instruments or specific protective equipment. And we want to the objective is to reduce occupational hearing damage to the lowest level as possible. Okay, information to be provided from the workers, and the most essential elements or the equipment is the ear protectors. Sometimes we have 2 levels. What is the meaning of 2 levels? The first level is what we call the first actions level. We still have the second actions level. Okay, under different actions levels, we have different requirements. Okay, the first actions level is daily personal noise exposures up to 85 dBA or above. This is the first actions level. And the second one is when the level is up to 90 dBA, please pay attention, this is the equivalence level, okay? This is the daily personal noise exposure, or in the short term, we term it as LEPD, okay? 85 and 90. The peak level actions use 140 dB. Okay, no one can survive under this one. Okay, the last one. How to check the daily noise, personal noise exposure level? We use this one. We call this one is the noise dosimeter. It's a kind of device that can help us to check the equivalence levels over the periods of time. As I told you before that, we need to follow some general requirements that what we need to do. There are 2 levels, first actions level and the second actions level. We define clearly the proprietor's duties or the employee's duties. For the first actions level, okay, this is not compulsory to bring ear detectors, but above the second actions level, this is compulsory, okay? But even this is not compulsory, workers can ask their employers to provide certain protection equipment to them, okay? So I could not go through one by one about this one, okay? If you are interested, you may refer to this one. What are the proprietor's duties and what are the employees' duties? I just want to let you know how to assess this one, daily personal noise exposure level. This one you learned it before in the first 2 lectures, is how to find the equivalence level. Reference to this one, equations, it is in terms of the pressure. Okay, normally we could write it in terms of sound pressure level instead of pressure, because when we use a sound level meter, we can find out the sound pressure level instead of sound pressure. And T0 here is 8 hours. Okay, this is a normal time durations for every day. And TE is the durations of personal exposures to sound effects. Okay, PA is the time variance value, and this one, the bottom one, is the reference value of 20 micropascal. To find out the LEPD, the daily noise exposure level, there are two approaches. The first one is to use equation. This equation, let us go to this one. This equation is exactly equal to this equation. Okay, one is presented in terms of sound pressure and one is in terms of sound pressure level. The second one is to use the nomogram here. Okay, I will let you know how to use this one. So that it means that you can either use these charts or these equations. Okay, it depends on what you like. Okay, from the nomogram, you can see that this is a symbol chart. This is the exposure level, the red one. Okay, on the left hand side, this is the exposure level. On the right hand side, this is the time duration. Okay, and in the middle, this is the LEPD. Okay, the daily exposure level. Okay, let me take one example to show how we can make use of these two approaches. For the first one, a person is exposed to a noise level of 103 dBA for 3 hours in a working area. The rest of the working day is 75 dBA. That can be lower. Okay, 75. It is below the first actions level. Okay, 85. So we don't care about it. Okay, even in our surrounding environments, the level is about 70. Okay, so that's we care about the first actions level. Okay, what is the daily personal noise actions level? If we want to find it out using this equation, it is very simple. Okay, T naught must be equal to 8 hours. Okay, this is a normal daily durations. And how about time? The time we just have one session, correct? This guy is subjected to 103 dBA for 3 hours. So that LPA, this is sound pressure level, is 103 dBA. And time, we just have one time session. Okay, 3. So the noise exposure level is 98.7 dBA in this case. It is so simple, okay? We just make use of one equations and then substitute all these ones to the equations. We are able to find out the answer. Okay, this one is not difficult. Okay, I'll repeat many times how to make use of this one. Okay, now let's take a look how to use this one, how to use these nomograms to find out the answer instead of using the equations. Okay, there are two major data. The first one is 103. Okay, the dBA. Where is 103? According to this chart, where is 103? This is 103 dBA, correct? Okay, when you read this line, the red one. Okay, this is 100, 101, 102, 103. Okay, and where is the time durations? When is the time duration? 3 hours, correct? Okay, let us refer to this green line. 3 hours is here. This is 3 hours. Okay, 2 hours, 3 hours, 4 hours, 5, 6 hours. Okay, what is the next step? The next step is that you draw a straight line to connect 103 dBAs to 3 hours. Okay, draw a straight line. When you draw a straight line to connect 103 dBA for 3 hours, there is an intersection point between this straight line and the middle line here. When you read the data, where is this intersection point? The intersection point here is about 99 dBA. Okay, this is almost the same as what we found using the equation. So you may make use of one of the approach to find out the correct answer. Okay, this approach is very fast. Okay, we just read the data directly from this charts. Even when you look carefully about this figure, there are some equations here. You can make use of these equations to find out the answer, the same answer here. Okay, T. This is the standard equations. T is the time durations. The time duration is 3 hours, and the noise exposure is 103 dBA. So that the fractional number here is F. It refers to a fractional number. It refers to 7.48. When you substitute this value into the second equation, you can find 98.7 dBA. The same answer. Okay, this is sample. We just consider one time duration. Okay. How about if we have a case like this? If a person is exposed to a noise level as follows. What is the daily personal noise exposure level? This guy is exposed to 112 dBA for 30 minutes, 108 dBA for 45 minutes, and 100 dBA for 90 minutes. Okay, 3 time sessions. When you use equations, it is not difficult. We just substitute one by one. Okay, we just have T1 session, T2 session, and T3 sessions based on this equation. Let's say in this case, you just plug it into this one. But I want to remind you, the time durations is in terms of minutes, so that you have to change it back in terms of hour, because the base value we prefer is 8 hours. Okay, so if you just substitute 30 minutes into this equation, it is not correct. Okay, this is the point I want to highlight to you. So it is not difficult. Okay, you just substitute this all time sessions into these equations, no matter how many we have. Okay, the final answer is 102.5 dBA. Okay, any problem about this one? But now, when we take a look on this one, how to make use of this nomogram to find out the results. Okay, let's take a look on this one. When we want to use this one to find out the results with different time sessions. Okay, 112 for 30 minutes, 108 for 45 minutes, and 100 for 90 minutes. What is the step? This is different from the previous one. Because when we refer to this nomogram, it seems that in each time we can only find out one data. Okay, how to do this one? Okay, let's take a look for the first one, 112. This is 112. Okay, 112. For 30 minutes, when you draw a straight line to connect the middle line here, please first find out the fractional exposure value here. The intersection points here, when you read the data here, is about 10. Okay, this is the first one. Okay, you can follow the same procedures. The second one is 108. 108 is here. 45 minutes. And the connection points here is equal to 6. Okay, you read it on the right hand side, F. Okay, this is about 6. Okay, what is the last one? The last one is 100 for 90 minutes. Please pay attention to this one. 90 minutes. The time durations, we don't have 90 minutes, but we have 1.5 hours. Okay, the fractional exposure for the last case is 2. And then please add all of them together. The total fractional exposure is 18. When you refer to the data 18, what we can find out? You can see that when F is equal to 18, the level is about 102 to 103 dBA. Okay, so that's when we handle the cases with different time sections. You have to first list out all the fractional exposure values and then add up together. Once you got the total fractional exposure, you can read the data directly from the middle line here. Okay, any problem about how to handle the cases for different time sections? We go to actually the key equipment. We would use it is ear protectors. For the ear protectors, to select and appropriate and approve the ear protectors, we refer to this BSEN standard. We could not go through the details about that. I just list out the full names of these standards to you, and this is a table to show that the variations across the 1 octave frequency band. You can see that this is the assumed protections. What does it mean? Assumed protection. It means that if we wear this ear protector under 63 Hz, it can be reduced by 17 dB. Okay, 17 dB protection. It means that you can help you to reduce some sort of noise effects. Okay. The whole document for this industrial guidelines is to protect our ears, to protect workers' hearing abilities. How to assess the hearing deterioration effects? We have some people created a term here is hearing deterioration index. Please pay attention. This is for very long-term durations, not just for 1 day or 1 week time duration. Okay. So when we calculate the hearing deterioration index, we may make use of this equation. Don't be afraid of these equations. This is very simple because when you refer to this one, we just have 2 parameters. One is L. L is the mean exposure level, and the T is here. T is the exposure years. Okay. That's why I call this one is a very long-term effect, not just for 1 day, 2 day. Okay. How to assess the hearing disability? Okay, let me tell an example for you. If a 90 dB exposure is for 25 years, and we assume that the working duration is 8 hours a day, what is the percentage of risk of hearing loss? What is the percentage of this one? Okay, we may refer to this figure. In terms of this figure, the vertical axis, the y-axis is the medium loss, is the how many percentage of the hearing loss, and this one is the percentage risk of developing a hearing handicap. First of all, we use this HDI. What is HDI? Hearing deterioration index. This is the standard equation. We do not need to do any integrations because we can convert it into a simple equation like this. Okay, because we assume that L is a constant value. So that's the exposure level is 90 dBA for 25 years. So HDI is equals to 59. Okay, this is just for the HDI, the hearing deterioration index. How to find the percentage of risk? Let's go to this figure. When you refer to this figure, okay, this is a curve, okay, and this curve shows the values on the values for HDI. Okay, this is 50, 55, 60, 65, 70. Okay, now we got the data. We got the value HDI is equal to 59. This is 59, correct? And then you draw a vertical line here and a horizontal line, and then you can find the results. The result is that under the conditions given here, the percentage risk of hearing loss is about 18%. This is 18%. Okay, to have 24 dB loss. Okay. So that if a worker under 90 dBA for 25 years, he may have the percentage risk of hearing loss of above 18% to have 24 dB loss. Okay, any problem? Please bear in mind that we could not make use of this chart hearing deterioration index to assess the normal durations. Okay, we just suffer from 1 week exposures for high levels of noise effects. Okay, this is it doesn't make sense. Okay, this is a very long-term duration. And there is a line here to demarcate adequate for speech recognitions and inadequate for speech recognitions. Under the conditions here, this guy is still adequate for speech recognition. Okay, this is the final page of this lecture. This is noise cancelling headphones. This is they make use of the active noise control approach for this one. There are different commercial brands for different products in our markets. In this one, actually, we have a microphone. The functions of this microphone is to sense the incoming wave, and then they have the noise cancelling circuitry. And this one, mainly. They are electronics inside this one. Inside the headphones, they can make use of the speakers to create an anti-sound effect to cancel out the incoming wave. And then the major properties is that we need to have a battery because this is an active control system. Without a battery, it cannot work functionally. Okay, but most of the time, we for industrial working environments, we just use a passive approach, not this active approach. Okay, and all the information for this in-class exercise I will give you back tomorrow for your revisions. Okay, let's get another break, and then we still have 2 questions for our tutorial tonight. The calculations from even the descriptive problems. I could suggest you just to review all my tutorial questions and even still Okay, we still have 2 tutorial questions tonight. The first question is about the Doppler effect. You may refer to the road traffic noise here. Okay, we have 4 cases. In the lectures, I told you that you need to identify which case we are going to study. Okay, and then you can pick up the correct equations for your analysis. Please pay attention. The arrows here, it doesn't mean that they are going to the left-hand side or right-hand side. Okay, it refers that they are going to the observer or moving away from the observer or something like that. So you may refer to this page to consider the first question. For the second question is about that the sample level on a rotating fan. Okay, so you may refer to the first illustrative example tonight in this lecture notes, industrial noise, to complete it. Okay, I think that you can complete it within 20 minutes. Okay, please.
我整佢標誌啊，係啊，好咧，呢個就時間6分嘅。嗰單嘢真係正式完，交付人，唔係交完跟住要補多錢，好似買咗入。即係攞嚟 都仲講嗰個槍彈都咁樣，唔係喎，佢哋轉頭發應該係離遠嚟。佢冇講就係係啊，呢個 receiver 先係因為你你話佢邊個時候會大用，你以為你話邊個時候大用？冇咩記得之前有白人細咗。即係 U 係嚟，因為佢先跟住上邊啲，佢哋都覺得即係大咗。最多30
Okay, let us complete these two questions. For the first question, we have a moving source problems on a well track, and the noise monitoring a stationary acoustic instrument is installed at either track. Okay, based on the information here, we know that the observer is a stationary instrument, and the source is a moving train, where you can detect a frequency of 0.98 times the frequency of the sound horn. Okay, when you refers to the lecture notes here, we have 4 cases. We need to define which case that is belonging to the current questions, whether the source is moving to the observer or the source is moving away from the observer. Okay, how to define this one? You may refer to this one, 0.98, okay? Because when you compare this one, it means that the detected frequency is lower than the observed original frequency. Okay, when the detected frequency is lower, what does it mean? The wavelength is longer, correct? When the wavelength is longer, it means that the train is moving away from the source. You can see this one. When the train is moving away from the source, okay, we have a longer wavelength, okay, but the frequency is lower. Okay, so the first one is like this. Because the detected observed or the observed frequency is just 0.98 times f. F is the original emitter frequency generated from the train. Okay, so that's why the train is moving away from the acoustic instruments. You can select the corresponding equations here. The velocity of the observer, okay, is equals to 0 because this is a stationary instrument. And the source, we don't know this one. V is given, okay, V is a typical value, is equals to 344. Okay, it depends on whether you want to substitute it or not. Because we know that 0.98 F is equals to this guy, so that we can follow this one to find out that US is equals to 7 meters per second. If I request you to find out in terms of train speed is kilometer per hour, you just use 7 times 3.6. You can find out the values in terms of kilometer per hour. So the tricky point in this question is whether you need to, we can define whether this is moving away or moving approach, is moving to the observer. Any problem? The F can be cancelled out on both left hand side and right hand side. Okay, question number two. Question number 2 is total noise can be created from a rotating machines. The numbers of raised here is 62. The rotational speed is 480 RPM against the pressure 170 PA and 1.7 meter cube per second. Please pay attention here, 1.7 meter cube per second. When you substitute into this equation, it becomes 1,700 liter per second. Okay, because the basic the reference value here is 0.47 liter per second. Okay, we need to determine the brake passing frequency and calculate the overall sound power level only. Okay, so that we need to consider the whole spectrum from 63 Hz up to 8K Hz. And this is a backward cleft brake, so that we refer to this row, the data presented in this row, okay? And the brake tone factor is 3. To determine which frequency we need to make corrections, it is up to the rotational speed and the numbers of brakes. Okay, solution. The first issue is to find out the brake passing frequency, 62 times 480 divided by 60. So the brake passing frequency is 496 Hz, okay? 496 Hz, it is in the range around 500 Hz. So the frequency lies in the 500 Hz octave bands within this range. When you consider within this range, you need to make a corrections factor 3 dB. To assess the sound power level. Okay, outside this frequency domain, you do not need to consider these effects. So let's say at 63 Hz, according to the table, the specific sound power level is 35. The flow rate is 1,700 liter per second. The pressure is 170, and BT is equal to 0. Okay, please pay attention here because this 63 Hz is not within this range, so that it is equal to 0. And Cn is given 4 dB. Okay, so it becomes 71.3 dB. Because we need to find the overall sound power level, so you still need to consider other frequencies from 125 Hz up to 8K Hz. The only difference is at 500 Hz, we need to apply for this correction factor 3 dB. Other frequency values, we do not need to make correction. Only this one, only at 500 Hz. Because all other values, they are not within the range 354 Hz up to 707 Hz. Okay, and how to find the overall sound power level? The overall sound power level, you just add from 63 Hz up to 8K Hz. This is the final result, 77.68 dB. Overall is the total. Okay, any problem about these two questions? Okay, your final examinations formats. In this year, I just made a slight change in the formats only, okay? But the questions types they are the same. They are similar to the past papers, okay? No worry about that. First of all, this is a closed book examinations. You cannot bring any lecture logs or reference books to take examinations. But please pay attention. You need to bring your calculators, okay? Because in previous years, many students they forgot to bring calculators. I don't know how to help him or her, okay? Although some students may bring more than 3 calculators together, they can share with them. Okay. Okay, in this year, the format is like this. First part is compulsory, total 40 marks. Total 40 marks, many descriptive questions and writing type questions, okay? Because I want to make a balance between the descriptive parts and the calculations parts. I don't want to insist too many calculations in these subjects. And the second part, there are 4 questions in total, but you just need to select any 3 of them, okay? Do not answer all 4 questions, okay? I could only count the first 3 questions, okay? Even you complete all 4 questions. So the second part, total 60 marks. You only need to select 3 of them. Each one is 20 marks. Many calculations, okay? Many. So my suggestion is that please review my tutorial questions and individual assignment questions. Okay. If you have any problems, you know when we'll take this exam. Yeah, 11th of December. Okay, at night in the evening. So during this period, if you have any problems, you may come to my office to discuss with me. Okay? And what else? One more. Even you don't know how to answer the questions, please try your best to write something. Okay? Please do not leave it blank. Okay? I can try my best to give you marks if you write something. But if you do not write anything on your answer book, the final result is just 0 mark. Okay? So try your best to write something on that. I could stand on your wheel to mark those questions. Okay, thank you.